Welcome back. In our last video, we looked at an example based off the expansion and evaluation of trig functions. We considered the cosine raised to the power of 5 theta, right? And we also said that we could also do that for the sine as well. Earlier, we had already discussed cos 5 theta and, of course, its corresponding sine 5 theta. If you have not watched that, please take a pause and go through the previous videos to consider that. So far, we have looked at the concept of complex numbers as well as complex functions. These two has been splitted out into two playlists, one playlist being on complex numbers and the other playlist being on complex functions, so that the playlists do not get too long for you to follow up. This would now signal the beginning of yet another playlist in the complex analysis series, which would be the playlist centered around the Green's theorem. However, for today, we will start off with the concept of the line integral. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now, for line integrals, of course, in calculus, this comes in at evaluations or integrations towards finding the area under a curve. Now, the same thing applies as far as complex analysis is concerned. Ideally, we can define the line integral and say, let T be a curve in the xy plane joining coordinate x1, y1 and coordinate x2, y2. We can then define the integral over c p dx plus q to y to be equal to the integral from the first coordinate to the second coordinate of p dx plus q to y, which means the integral on that curve is essentially the same thing as the integral from the first coordinate to the second coordinate, with those coordinates now serving as the bounds of the integral. Of course, p and q are functions of x and y. So we can call this integral the line integral. So essentially, the result of the line integral just seems like the shadow of a two-dimensional shape as much as it can, because of course, remember that p and q are in terms of functions, are functions of x and y. Now, there are some very, very interesting properties that we can talk about for the line integral. We'll take just two of them. The first property in this regard can be written as, if you have the integral from x, y, x1, y1, to x2, y2 of p dx plus q dy, then you could split the integral based off each integration variable, which is, you'd have this as integral x1, y1, x2, y2, p dx plus the integral x1, y1, x2, y2, q to y. So the integral can split based off those two integral variables. Similarly, if you have the integral from x1, y1 to x2, y2 of p dx plus q dy, you could decide to break the journey by a particular stop point, such that the integral of those two new destinations will total the full destination. What does that mean? I could have the integral from x1, y1 to a new coordinate x3, y3 of p dx plus q dy, and then when I add to the integral from x cubed x3 y3 x2 y2 of p dx plus q dy, the sum of these two integrals will give me this, right? In simple terms, if you were to look at it analogically, you could have that you're saying if you could move from a distance a to b, it will still be the same thing as if you moved from a to c first and then from c back to b, right? So you could look at it like your distance from your house to a mall, for instance. What if you now decide to go from your house to a bank first to withdraw before you then head to the mall? What it's saying is that the total distance you cover from your house to the mall is still the same as the distance you cover from your house to the bank and then from the bank to the mall, right? Now, while of course there might be a little bit of discrepancies when you now talk about your distinct destination traveled, this is not what is being covered in this regard. What is covered in this regard is, do you still start from the same start point and end up at the same start point? The kilometers traveled is not our concern as far as this is involved. What is our concern is, do you start at your house? Do you end up in the mall? Yes, you do. Then it means you still refer to the same target point. So this is the representation of the line integral as you have it. Now the line integral, the reason why we have to consider the line integral is it is very, very, very important to our study into how to utilize the Green's theorem. So now that we have discovered or we have talked about the line integral, we would go ahead to state the Green's theorem, right? And then in subsequent videos, we'll then put the Green's theorem to use in terms of examples. So now let's state the Green's theorem. So the Green's theorem talks about how you could split your integral over the curve into the integral based off the parameters of the function, which is your x and y. So let's see. So let C be a simple closed curve bounding a region R, and let AX, AY, and their first partial derivatives be continuous in the region R. Then the integral over C of AX dx plus AY dy will be equal to the double integral over the region del x ay minus del y ax dx to y. So this is what the Green's theorem tells us, which is the integral over the curve of ax dx plus ay dy is going to be the same thing as the double integral over the region of the partial derivative of ay with respect to x minus the partial derivative of ax with respect to y dx dy. So this would refer to the standard statement of the Green's theorem, right? Hereinafter, we will then take in examples on how to utilize the Green's theorem. As always, make sure to like, share, and subscribe, and turn on your notifications so that you do not miss any of our videos.